Hey guys, this is video 2 of our 2-video series for section 16.6 on surfaces and areas. Hopefully if you're watching this now, you've already seen the video on surfaces. Last time we focused on how to parameterize surfaces or express three-dimensional surfaces in terms of parametric equations. This video I wanted to focus a little bit more on areas. Now, one comment that I'll go ahead and make here is why focus on areas? Well, it's kind of a natural extension for some of the ideas that we've seen before with previous integrals that we've developed. One of the things that keeps popping up a lot is each new differential that I introduce you guys to. dA for area, dV for volume, d(s) for arc length. Each of the differentials that I've showed you guys for scalar functions, it has this nice pattern where if you integrate one over something, related to one of those integrals, it measures stuff, right? So if I'm taking a double integral, 1dA, this is going to find an area measurement of whatever region I'm integrating over. If you are taking a triple integral of 1dV, this measures the volume of the region you're integrating over. If you take a line integral of 1ds, this is going to measure the arc length of whatever curve you integrated over. Now, we just talked about finding parametric equations for surfaces. A natural question would be, can we find a way to measure surface area with integrals? Is there some sort of differential that we can maybe build that we integrate one with respect to that guy, and it gives me surface area back of the surface that I just integrated over? Well, yeah, there is an integral that corresponds to that, and if I'm wondering about how to develop that, the idea behind how we build that integral is as follows. Okay, so obviously the answer is yes, we can build integrals that measure surface area. We construct the idea, okay, starting with approximation, right? So I'll say starting with my approximation of my surface with something linear, right? All of the integrals that I've shown you guys before, we usually build these up in terms of what does the approximation look like, what do the differentials suggest for me, and if I take a limit, this is going to suggest some sort of integral that I should take that no longer gives an approximation, but a true area. Now, when I take my approximation of my surface S, the linear thing to approximate surfaces with is planes. So I am going to chunk up my irregular surface S. These surfaces, they might not be nice, round, or nice, geometric regions. They might not be flat. They could have curves. They could have irregular edges. So if I start out with one of these things and I don't have a nice geometric formula for it, well, we can find an area of flat things. Maybe it might be messy in some cases, but, we can figure it out, okay, with our approximation here. So what I'm going to go ahead and do is, again, think about what happens if I chunk this guy up into a bunch of flat pieces, and approximate by taking my sum of my areas of each of those little pieces that I chunked this thing into, okay? Now, before I really jump into that, before I really jump into building that integral in the first place, I want to make sure that this notion of approximating by planes is something that I can do. So can I find, say, tangent planes for my surface? And yeah, we can do this, right? So it is a worthwhile question to ask, make sure that we actually can reasonably find planes that could do an approximation like this. How do we find them? Well, remember, anytime that you're trying to find a plane, you're going to need two things, okay? Given some sort of normal vector, that was one of the things that you needed, and also a point on the plane, Okay, so let's specify a point on my plane. We'll call this thing x naught, y naught, z naught. Your plane equation looks like this. Okay, you have a times x minus x naught plus b times y minus y naught plus c times z minus z naught, and this has to come out to 0. Okay, so this is my plane equation. We still need to be able to use this if we're finding tangent planes. Now, before when we talked about tangent planes using explicit functions to describe our surfaces, okay, we called them linearizations. We use them to approximate things a couple sections ago. We have a slightly different approach for how to get my a, b, and c, and potentially my x naught, y naught, and z naught here. So I have to be a little bit careful about what formula I'm using. I'm actually going to stick to this one. I'm not going to, give you guys some weird L thing to memorize. We're just going to do this the old-fashioned way and come up with a normal vector and a point and just use the OG plane formula. So I need to worry about my point first and foremost. There's one of two ways that point could go. Now, given some sort of parameterization, let's say r of uv, you will need to know two things. Not just the point that is on your plane, but you are going to need to know whatever u naught, v naught, in D, and you are also going to need to know your corresponding three-dimensional, if I could spell this correctly, corresponding 3D point on your plane, which is what happens when you plug that in. So just r of u naught, v naught. Okay? Now, whenever you're asked to find or if you are asked to find a tangent plane, given a plane parameterization, either you're going to be given that u naught, v naught, and then you can substitute it into your parameterization to get your three-dimensional coordinate for your point of tangency, or vice versa. Maybe you might be given your point and you'll have to use your parameterization to solve for whatever this u naught, v naught was. Okay, so this r of u naught, v naught, that's what we'll use as my point on my plane. Now, the reason that I need both of these and not just the point on the plane and I can call it a day, the reason that I need both of these is this. For your normal vector, what I want you to do is basically take your partial of your parameterization with respect to your first variable, and then I want you to cross it with your partial with respect to the other variable. Okay? And we'll go ahead and evaluate this at that point, u naught, v naught. Right? Now, kind of the idea here is this. If I have my surface and I've got my point of tangency that I'm interested in taking this plane at, well, when you take that partial with respect to the u component, you're going to get some sort of a tangent vector to your surface at your point of tangency. If you do the same thing with your v vector, you are going to get another vector that is tangent to your surface at your point of tangency. And what does the right-hand rule say that we do? Well, when you cross those two vectors, you are going to get your normal. Okay, so if I take my ru and I cross it with my rv, this thing is going to actually give me my normal vector. Okay, so this is why we want to take that cross product. Some comments here that I will go ahead and make before moving on to actually showing you guys an example involving this. Comment number 1, in this case, your order is not so important. Again, if you cross two vectors by the right-hand rule, it's going to tell you the direction that the result points. If you do this backwards, so if you maybe did RV cross RU, we'd get a sign error. We would get a vector pointed 180 degrees in the opposite direction, but that would still be perpendicular to whatever plane that we were looking for, okay? So, I'll go ahead and note if you do RU cross RV, RV cross RU, let me get my writing straight here, RU, this guy also works in a pinch. Another comment that I'll go ahead and make here is I'm describing this in terms of some parameterization, R of UV. We might use other variables than U and V, okay, so be on the lookout for that. And it's not the variables that are terribly important here. It's really more the pattern than anything else. We've seen a couple examples where maybe we're using stuff like phi and theta. Later on, you might run into things that have like r and theta. I'll distinguish that by the fact that these vector functions should have hats on them. So that would make it a different variable. Just keep in mind, it's the pattern that's more the important thing than it actually is, the fact that we're using U and V here. Okay, so in general, if you've got this point on the plane, if you take partials, cross them, and plug in your point from D, you'll still get a point on the plane and a normal vector. And once you have that point on the plane and the normal vector, all you have to do is use the plane equation, right? So just dust the plane equation off, and you've got your equation for your tangent plane. So let's actually try this out, okay? I will dust off an example that we did in the last video. We talked through parameterizing the unit sphere, so we got back this equation right here, and I'm going to ask that we just find an equation for a tangent plane at the point 1, 0, 0. Now, if I'm being totally honest, the efficient way to do this problem, you can probably just eyeball this and take a stab in the dark and guess at what the right answer should be, but let's see if we can actually confirm that we get that answer back, right? My unit sphere at this point 1, 0, 0, it's right here. If I had to guess at what a good tangent plane would be here, this is probably just going to be this vertical plane where x is equal to 1. So let's see if we can actually get that thing back, right? Let's see if we can actually compute this out using the method that we just described. Right, now, for that first part, I said we not only needed the point of tangency, and here my point of tangency, my point on my plane, this is given. We're using 1, 0, 0. I said that we not only needed that, but we also needed to know what UV coordinate and D corresponded to that. Now, here we're not using U and V. Like I said, we might not be using those all the time. The parameters that I'm using this time are phi and theta. So what I want to ask is basically what phi theta coordinate corresponds. Okay, what pairs up with that 1, 0, 0 point? Now, there's a couple ways that you could go about doing this. We could sit here and try to solve, right? Like, I could set up a system of equations, this parameterization has to match up to 1, 0, 0, so I could set cosine phi equal to 0, and sine phi sine theta equal to 0, and sine phi cosine theta equal to 1. And I could try to solve that system. Like if you have cosine of phi equal to 0, there's a limited number of values of phi that'll make that work. You could test out the consequences of those and see if you can whittle out what theta has to be. I'm going to be a little bit smarter than that here, though. This is an example that we did start out last time with the idea in mind that we used spherical coordinates to get back this parameterization. So if I'm thinking about my spherical coordinates for that, well, this point, what phi and theta does it correspond to, right? Well, if I'm worried about phi in spherical coordinates was just the angle that we come down off of the positive z-axis. That looks like 90 degrees right there because it goes from the positive z-axis to the positive x-axis. That means that that first component is just going to be pi over 2. If I'm worried about what theta that point corresponds to, remember theta was kind of giving your lateral position on the xy plane in terms of angle off of the positive x-axis. your theta here is just going to be 0, right? So if I think about this in terms of my spherical coordinates, we've got the point back pretty fast, but we could check that that actually does match up with this 1, 0, 0 point, right? Like if I take sine of phi, so sine of pi over 2, times cosine of theta, which is cosine of 0, that's 1 times 1, I get 1 back. And, you know, we could plug this in to the other components and check that we do get 0 for both of those as well. So this phi theta actually does correspond to that xyz coordinate. Okay? Now, we've got the point of tangency. We've got the point in the domain of my parameterization that corresponds to the point of tangency. The other thing that I said that we needed was my normal vector. Right? Now for the normal vector, there were 2 things that we needed to worry about computing. Okay, first off, I needed to find, before if we were working with R of uv, I said find RU cross RV. We don't have U and V here, we have phi and theta. So I'm really worried this time about R of phi and R of theta. Now I'll do R of phi first. If I'm looking up at that parameterization, my partial of this with respect to phi is just going to be cosine phi cosine theta, cosine phi sine theta, and then minus sine phi. Now, a comment that'll save me a little bit of time and a lot of writing. I said that I wanted ultimately R of phi cross R of theta evaluated at this point of tangency. I can also substitute that point in right off the bat, and then that's going to give me some less stuff to write down and substitute in later. So here, if I actually evaluate that to figure out what this vector is at this particular point, so not just my arbitrary tangent vector somewhere random on the sphere, but at 1, 0, 0 in particular, if I actually plug that in, it's not 1, 0, 0 we're plugging in, it's R of phi theta. This is why we found that corresponding spot in the first place. If I substitute in my phi, the way we've been writing this, phi comes first. That means I need cosine pi over 2 times cosine theta in this first slot. Cosine of pi over 2 is 0. So that'll kill off both of these first terms. And then for this last one, I need minus sine of phi. That's minus sine of pi over 2. I get minus 1 there. Now I needed both R of phi and R of theta, so I'll go back and find R of theta now. You'll notice my sine phi, that's going to hang on as a constant coefficient in my first component, but the derivative of cosine of theta here will be minus sine of theta, so this first term is going to be negative. For this next one, I'll hang on to that as a coefficient, and I'll get a sine phi cosine theta. And then for this last guy, there's no thetas in it, so this will totally drop off. And same trick as before, I'll save myself a little bit of work and just evaluate this at the point outright instead of taking my big nasty cross product with all of those trig terms in it. And if I substitute this in, notice in this first piece, my sine of theta has me taking sine of 0. That will drop off. My sine of phi is sine of pi over 2, which is 1. My cosine of theta is cosine of 0, which is 1. Product there is pretty straightforward. And then I have a constant term at the end. So, my normal vector, this is actually going to be equal to whatever happens when you take R of phi and cross it with R of theta and then evaluate that at pi over 2, 0, but we've already done that evaluation. So really what we're worried about here is crossing those two vectors that we just found. Now, if you still need to do your scratch work, that's totally fine, but I'll go ahead and give you guys the spoiler here. If you work out that cross product, you're just going to get 1, 0, 0. That's it. Now, when I go to actually, use the information that we've got, right? We've said that we have this point on my plane, 1, 0, 0. We've said that we've got this normal for my plane that is 1, 0, 0. Again, what these are going to correspond to are my x naught, y naught, and z naught, and for my normal vector, my a, b, and c. I just need to shove these guys into the plane equation, right? So again, my plane equation looks a lot like this guy right here. I just have to remember the plane equation to perform this substitution. So I'll basically get a 1 times x minus 1 plus a 0 plus not equal plus a 0 times y minus 0 plus a 0 times z minus 0. And it should be pretty clear that we get a lot of cancellations here. So ultimately, looks like x minus 1 is 0, or the plane that we predicted that we got in the first place. Okay, so this method actually does check out. We do get the plane that we expected for my tangent plane at the point 1, 0, 0 on the sphere. Now, with that said, the primary reason that I brought up these tangent planes in the first place is just, can we take tangent planes to these parametric surfaces? Now, why did we care? Remember, the whole point of this was I wanted to ultimately build an integral that helped us figure out surface area. Okay, so, all that we did before, totally well and good. How do we actually translate tangent planes to helping with surface area? Because, just because we made it flat, what do we do with it now? We know flat things are easier to find area of than, irregularly shaped things, but how? Well, one thing that we are going to need to dust off is the area formula that we found way back in the cross product section. So, we're probably talking like first couple weeks of class here. It's been a hot minute. Remember, from that section, I gave you a formula that let you compute the area of a parallelogram that was determined by two vectors. Now, I've got this big messy, diagram going on here. Oops, this should not be an F. This should actually be an R. Let me fix that. I've got this big messy diagram here, but the ultimate point was this. We said that we wanted to try to approximate our surface with a bunch of parallelograms. Well, I can think of those vectors that we were kind of using before, something kind of similar to our, tangent vectors. If I think of those guys as determining little bits of parallelograms on these surfaces, what I could do is find the area of each individual one. And then once I found the area of each one, I could go ahead and sum across all of my areas, right? So here, again, what I'm doing is we basically just want to approximate S with these parallelograms, sum up my areas, and then that'll give me an estimate, okay? So this will give me an estimate of my surface area. Now the catch is, this is just an estimate when you do that. Okay, if I were just to chunk this into a bunch of parallelograms, it's not the true surface area of S. If I wanted to make that a better approximation, well, our usual trick is we use limits, and we try to make those approximating pieces smaller. It's hopefully not too hard to imagine that if we used smaller and smaller and smaller parallelograms to approximate this thing, my error would shrink down to 0, at least for a nice smooth surface. And then, I would get a true surface area back, right? So here what I want to do is that sum, if I actually take my limit, as my size of my parallelograms shrinks, okay, so as my size of those things, goes to 0, I'll go ahead and just say that it shrinks. That limit is going to give me my true surface area. Okay. Now, I don't know whether there's this random A here. Now, as far as that idea, how do I actually set this up? Okay. So that's my true surface area. How do I do the area of one of these parallelograms? Right? So let's actually try that. If I want the area of one of those parallelograms, and I'll just kind of draw the picture here to mimic what it is that I'm trying to find in that diagram. Well, we've just said your area is going to be this cross product of whatever vectors determine that parallelogram. Okay, so my cross product of vectors on the sides of that parallelogram. And once you take that cross product, we need to take a magnitude, right? That was part of my formula up here. You can't just cross them and leave it. That'll give you a vector value. Vectors can't describe area. You need a magnitude of it to make that thing into a scalar. So, what are these vectors, right? What are these vectors that I've got on the sides? Now, the reason that my diagram is so complicated and includes my UV region here and my pre-image D, the reason is this, okay? I'm trying to give a little extra context for me finding these vectors. What I've started with, if you think about this UV region, is I've got some sort of chunk of domain here that when you plug it into R, it spits out your surface S. So that's point number 1 to observe about this diagram. Point number 2 to observe about this diagram is this little corner that my parallelogram is kind of emanating from. And that's corresponding to some sort of U0, V0 coordinate that I have marked in this UV plane. Okay, so that corresponds to this point here. Now, what you can do is think about the fact that if I have maybe a pair of vectors over here in my UV plane, you know, maybe that determines a square or a rectangle or another parallelogram. You know, if I think about it determining maybe a rectangle here, what I could do is think about each of these two vectors as having endpoints that I can track where those vectors go on my surface. So, you notice this U0, V0 is the starting point for this bottom vector, but the ending point is actually this U0 plus delta U, comma V0. So I've got an initial and a final point, okay, an initial and a terminal point for that vector, and those 2 points will map forward by R to this surface. So that means that these will actually correspond to an initial and a terminal point over here on this vector. And I've designated this accordingly, you know, that U0 plus delta U comma V0 that I was talking about. This is where I substituted into my function R. Again, I don't know why I'm calling these guys F's here. These should be R's. Sorry about that minor mistake here in my diagram. Let me fix that really quickly here. F of U0, V0. There's my axis, and for this last one, this is an R. Okay, so I've basically got my initial and final points on my surface here. Let's use those to help me figure out my vectors, right? Any vector is just a final minus initial point, so let's check what my final and initial points were. Right? I basically want this R of U0 plus whatever term minus this R of U0 plus whatever term. And that'll be my first vector. So here is that first guy. My final point minus my initial. And that is going to be a vector. I'm going to leave off the additional hats here. Okay, do note that will be a vector result if I'm doing final minus initial. And then I said that I wanted to cross the two vectors. Well, here's going to be the other final minus initial. Okay, so my other final minus initial looks like this guy. Which is kind of a mouthful. Now comment, this already looks kind of messy, and you might be a little bit hesitant to add additional clutter to this, but I'm going to tweak this guy just a little bit. What I'm going to go ahead and do is this. Okay, first off, you'll see me basically copying and pasting this because I'm going to leave a lot of this by and large unchanged, but there are two minor additions that I will make here to this expression. Okay, and those two minor additions are going to be this. For this first piece, I'm going to multiply by something. Okay, for this first piece, I'm going to go ahead and tack on a delta U divided by a delta U. That's ultimately going to cancel and not actually do anything, and delta U is a scalar, right? So this was just whatever quantity I added to get from U naught to the second point. So multiplication, division by a scalar, not going to change anything. I'm going to do sort of the same trick over here, except for this time I'm going to do it with delta V. So I've got a multiplication by delta V and a division by a delta V. Now, the reason that I'm doing that is this. If I consider these bits that I have as fractions here, in the limit, okay, as my delta U and my delta V go off to 0, those fractions are going to look a lot like the following. Okay? The delta U that I have over here, that's not really going to change so much, but this expression here is pretty much the precise way that I defined how to take partial derivatives with respect to the first component. You're just altering the first component by some scalar amount, and then you're dividing that out. This is totally a U partial of R. And then what I end up crossing this thing by is this thing, since I used delta V instead, and I had changed my V component, this is just going to be a V partial of R. Okay? Now, a final comment that I'll go ahead and make here, now that we've simplified the bejesus out of this, some other comments that I can make are this. One, those scalars, even though you're multiplying them by these vectors, we can pull scalars out of cross products, so you can just think about this as RU cross RV with a delta U, delta V on the end. That is totally kosher. Another comment that I'm going to go ahead and make is if we took that limit as delta U and delta V were going to 0, well, going back to my diagrams, when delta U and delta V go to 0, that basically sends the endpoints of those two vectors in towards this initial point. That's going to shrink the size of this ultimate parallelogram that I'm getting back here. So taking that limit is going to give me something that'll build my true surface area. Okay, and these differentials on the end, this is really going to suggest that my area looks like this guy. This is what I'm integrating for my, my surface area. So my area integral, in the end, if you boil through all this work, it should come out to the following. Right? We're really just taking, some sort of RU cross RV, du dv, or maybe dv du, but certainly over whatever region that we had in the UV plane. Okay? Now, if the derivation confused you, if you were totally lost there with what was going on, and you really just want to figure out how to compute surface area without thinking too hard about it, here is where we tune back in. Okay? If you're just worried about the formula, you've got a surface S, you figured out the parameterization for it, or you were given the parameterization for it, including a domain where that parameterization lives. If you want the surface area of that thing, this expression right here is what we're looking for. Okay? This other bit here about covering once, make sure that you don't have your parameterization set up so yet you're lapping over sections and covering sections multiple times. As an example, like when we had that sphere parameterization, if you let your theta range outside of 0 to 2 pi, you're doing multiple laps around the sphere and you're counting surface area twice or possibly more times. So we don't want to avoid that. If you only hit each point on your surface with this parameterization once, this is our go-to for computing surface area. Now, a comment that I do want to make here is pay attention to these variables. The way that I'm phrasing this, I'm assuming u and v are my variables, so that means u and v are the partials that we end up taking of that function. So I'll go ahead and make the observation that if your parameterization, if this guy is r of uv, that means that dA is either going to be du dv or dv du. Now, the reason that I point that out is this. I've said before, we aren't always using u and v. You might see a parameterization in terms of a different variable. So maybe we might see phi and theta. Maybe we might see r without a hat and theta. Make sure that your variables match. Okay, that's just my key point here. So make sure your variables match up. I don't want you guys to, try to set this up as, I took a u partial and a v partial and we're doing dx dy on the end here. That's not it. So I'm not assuming that dA is always dx dy or dy dx. We are using a dA here that lives in the uv plane. If we have a uv parameterization, your dA is going to be a differential that lives in the phi theta plane if you have a phi theta parameterization. So just pair whatever those two differentials are with whatever your parameterization used as your variables. I'll actually try this really quick, okay? And I'll do another example that we kind of had looked at before. The cone, r of... Here, the parameterization I'll try is r theta. So this is a parameterization that you can get back for a cone if you want. Restrictions r between 0 and 1, phi between 0 and 2 pi. You could set this up, if we had done the cheater standard parameterization as something like u comma v comma square root of u squared plus v squared. Or if you apply polar coordinates to that parameterization and change up your intervals, this is what we got instead. Now, if I want the surface area of this thing, well, I can just try to chuck this into my formula. Okay, so my formula here for these variables, right? We're not necessarily using u and v. For these variables, I'm basically going to want to set up whatever my r theta region is. Okay, so this is my r theta region. I'll go back and fix that later. But basically wanted the magnitude of r crossed with r theta dA. And again, this is for an r theta region here. We're not using x's and y's. And then the other thing that I'm going to point out is, yeah, we're using r's and thetas. You don't necessarily have to tack on an r, dr, d, whatever. We are starting in these variables. We are not converting to them. We have already done that. So when you go to rewrite this DA, don't try to throw on an additional R. We're already starting here, so there's no conversion needed. This is already, a DA, and we're already thinking about that in terms of these two variables. So the rest of this is just going to be plug and chug, right? So here, let's go ahead and I'll save writing my bounds in until later, but let's take these partials, right? So if I have R, means I need a partial of this thing with respect to R, I'm going to get cosine theta, comma sine theta, comma 1. And if I want a partial of this thing with respect to theta, I'll have a minus R sine theta, a R cosine theta, and then the derivative of this last piece with respect to theta is just going to be 0. Okay, so here, if I need to actually write out my scratch work for this, I'll go ahead and do that, for evaluating this cross product here. That was the components from my first vector with the first one repeated. Here are my components for my second vector with my first component repeated. If I go to actually take that cross product, what I should be getting is this. In my first component, I'll scratch out those columns and think about my products of diagonals. This first piece is going to look like a 0 minus R cosine theta. If I scratch out my second column and look at my products of diagonals over here, this is going to be a minus R sine theta. Minus 0, I'm not even going to write that in. If I look at my third column and scratch that out and look at my remaining products of diagonals, here I've basically got a R cosine squared minus a negative R sine squared. So really plus R sine squared. Which, if I want to clean that up into, something that I'll need to take the magnitude of in a moment, I don't need to write the pesky 0 again. And another observation that I can make is if you factor an R out of this end component, cosine squared plus sine squared is 1. So really you may as well just think of that as having an R there. Okay? So at this point, we got the cross product taken care of. We still need to take the magnitude. The magnitude is going to have me take the square root of the sum of squares of each of these components. I've got an R squared cosine squared theta term, an R squared sine squared theta term, and an R squared term. And if I'm applying the same exact comment that I made before, if you factor an R squared out of this first piece here, the cosine squared plus sine squared is just going to give you 1, okay? So that little bit there, that's just going to simplify to R squared, okay? So you've ultimately got an R squared plus an R squared in this integral. And this is the same thing as if you just have, a2 R squared inside of this integral that we're taking. Now, at this point, we've cleaned this up enough. I'm going to stop being lazy. I'll actually write in these bounds and what my differential are. Again, to reiterate, when we set this up, we said that the dA here, this was referring to an R theta region, so that means I either want dr d theta or d theta dr. There is no additional R that I'm adding in. I am not converting this to polar. I'm not necessarily looking at any things here that I need to replace with other variables, so there's no conversion. This is just a dr d theta that's going on the end. Okay, so if I do that, okay, this is not a polar conversion. We are starting in these variables, right? So we are starting in r theta, so there is no need for an extra r here. Okay, just a dr d theta. And then I have to match up the bounds to that. Okay, the inner bounds were the ones on r. Okay, I told you guys r stuck between 0 and 1, theta is between 0 and 2 pi. So if I do that, this is what I'm integrating. And I'll keep in mind that since my r is all positive values here, I don't have to worry about anything wonky happening with the square root. I can actually just simplify this as root 2 times r. Okay, I don't need to keep the r inside of the square root. And this is going to make it pretty easy to antiderive, right? So your antiderivative is just going to be a root 2 r squared over 2, evaluated between 0 and 1. If you evaluate those bounds, this looks like a root 2 over 2 that I need to integrate with respect to theta. So really I'm getting a root 2 over 2 theta that I have to evaluate between 0 and 2 pi, or root 2 over 2 times 2 pi. And if you want to clean that up a little bit, root 2 pi should be your end result here. Okay? Now, that out of the way, I'll give you guys a note, final comment here for these parameterizations. If you want to deal with these things, if you want to find surface area of something where I've gotten, you know, let's say I give you guys a z equals f of x, y, you don't necessarily have to jump to finding a parameterization and then jumping through all these hoops. I'll give you guys a little bit of a shortcut if you actually started out with the explicit function in the first place. If you use this parameterization, you know, this is going to turn into a 1, 0, u partial. And then, you know, your RV is going to turn into a 0, 1, v partial. And then when you go to actually set these up here and take that cross product, you know, what you'll basically get is this. And I'll just kind of give you the spoiler here. This is going to be a minus fu in this first component. In the second component is going to be a minus fv. And then in the third component, you're just going to get a 1. When I go to take the magnitude of that, I don't necessarily need to hang on to my signs. I'll just get a, you know, fu squared and an fv squared and a 1. So what I could have done in the first place is this, knowing that I get a direct link to my partials. What this suggests is if you want the area or surface area, okay, if we want my surface area of z equals f of x, y on some, you know, domain D of x, y values, I'm not even going to bother with a parameterization, okay? All this is suggesting is take a partial with respect to your first variable and a partial with respect to your second variable, right? So what I could do instead of the cross product and magnitude is I can just set up this much simpler integral, right? So fu squared or fx squared, if I'm doing this in terms of my original variables, and fv squared or y in terms of my original variables. Okay, and I can just set up this guy. Okay, so this is an alternate formula that you could be using if you have a slightly different surface. Okay, now I'm going to go ahead and just do this last one really quickly here, see if we can figure out the surface area of this section of plane in the first octant. We do need to figure out what the D is for this particular setup, so I'll go ahead and sketch this out. We've used this intercept technique to figure out what the surface looks like a number of times, so I'll go ahead and sketch this real quick. If you substitute in y and z being equal to 0, you get your x-intercept, which is 6. If you substitute in x and z equals 0, you can solve for your y-intercept, which is 3. And if you substitute in x and y equals 0, you can get your z-intercept back, which is 2. Okay, so really what I want is my surface area of that triangle in my, set up as an integral. Now, comment, this is not expressed as a z equals f of xy expression right now, so I can go ahead and fix that. If I want to express this as z equals f of xy, we just got to solve for z, right? So I can think of this as 6 minus x minus 2y, the whole thing, divided by 3, or 2 minus x over 3 minus 2y over 3. Okay, that's my function. And what I said that we could go ahead and do is, if I wanted to think about setting up my formula this time as just my square root of my x partial squared plus my y partial squared plus 1, all I need is to figure out what collection of xy values this thing lives on. So really, I'm worried about what xy values these are. Okay, so this thing right here, that set of xy values, that's my D. Okay, so I'm going to go ahead and just sketch that out really quickly here. If I think about that as providing my, D region that I want to integrate over, well, I can set this up pretty easily as a type 1 integral, so I'm going to just copy this over for the moment. If I set this up as a type 1 integral, that'll be dy dx that I want to treat this as. We can notice that the slope on this guy, this top curve, this has a rise of -3 and a run of 6. So this is ultimately going to be a slope of -0.5. It's got a y-intercept of 3, so it'll give me a -0.5 x plus 3 as my upper bound. And then on the bottom bounding curve here is just y equals 0. Okay, so bottom bounding curve there. And then we can also very clearly see my x bounds go from 0 to 6. So now I just need to actually compute these partials to grind out the rest of this integral. Okay, so if I do that, what function was I looking at in the first place? Well, this thing is what I'm treating as my f of x, y over here. So this plane was where I wanted to pull my partials from. If you take your partial of that with respect to x, we're getting just -1/3. If you take your partial of that with respect to y, this is -2/3. And then I have to tack on a 1. So the rest of this is going to be mostly algebra for us. We're getting all constants on the inside of that square root, so this shouldn't ultimately be too bad of an integral to take. Basically got a 9th plus 4/9 plus 9/9 here inside of my square root. So that'll be a root 14 over 9 when I go to simplify this thing. Or root 14 over 3 if you actually reduce that square root of 9. And this is a pretty straightforward antiderivative from here. We're just anti-deriving a constant, so I'll get a root 14 over 3y that I have to evaluate between these two bounds. If you substitute in the top one and then subtract off what happens when you substitute in the bottom one, well, you've just got this root 14 over 3 that I'm hanging on to, multiplied by this line equation. And now I can go ahead and antiderive. This is a single variable calculus problem at the moment, so no fancy Calc 3 stuff right now, just power rule, so minus x squared over 4 plus 3x, evaluated between 0 and 6. So from here on out, you know, really we're mostly just worried about substituting the 6 in. And you should get over here minus 9 plus 18. Overall, that'll simplify to 9 inside of the brackets. We get 3 root 14 back.